All right. Thank you for that welcome, and I appreciate the invitation to join you all today. I trust you can see my screen, and I'm going to be talking today about tall mass timber construction per the 2021 IBC. The IBC is the International Building Code, which is a little bit of a improper name for it. It is the building code that is used across the United States. Each state will adopt a version of the International Building Code, and it gets updated every 3 years. And we're going to be talking about what is currently the most recent edition of that code. And we can skip these slides. These are not as exciting. So today, what I'll be discussing will include some of the work of the Tall Wood Building Ad Hoc Committee that was convened by the International Code Council. The International Code Council is the organization that publishes the International Building Code, or IBC, that I mentioned we use in the US. I'll talk about some of the work of the committee, some of the testing that was done, and then the fruits of their labor, the resulting code changes that were implemented for these tall mass timber buildings in the 2021 edition of the code. And before I get going today, I want to emphasize that we're going to be talking about mass timber buildings. These are buildings that are going to be built from large members, including cross-laminated timber, CLT, glue laminated timber, nail laminated timber, members that have a certain size, typically on the order of, I have to check my metric, I'm sorry, I know these in inches. We're typically going to be on the order of 150 millimeters to 200 millimeters in cross section. So these are fairly stout members. Traditional wood frame construction in the United States has leaned towards a product called conventional light frame construction, which we see illustrated in this slide on the right. And these are members that are repetitive members that are spaced close together. So in this illustration, they're probably on the order of about 16 inches on center, which is about 40 centimeters apart. These members are relatively small in cross-section, approximately 50 millimeters by 150 millimeters, give or take a little bit. And the maximum height we would see on buildings like this would be roughly 4 to 5 stories. Mass timber buildings have very little in common with these types of buildings, aside from the fact that the product was made from something that was once harvested from a tree. As I mentioned, mass timber buildings are going to be constructed differently from a structural standpoint. The members are going to be much larger, and these buildings can be much taller. So today we're talking mass timber and not conventional light frame, and emphasizing that these two structural systems do behave differently. Another historical wood frame system that has existed in the United States building codes for a number of years, probably even before we had building codes really, is what's known as Type 4 heavy timber, or Type 4 HT. And this is closer to the Type 4 mass timber buildings that we're going to be talking about. These heavy timber buildings are going to be made of members that are on the order of about 150 millimeters square, sometimes even larger. These buildings have a historic root in the old industrial type buildings that we would see a lot of in America, where the interior of the building would be built with very large cross-sectional timber members for the floor joists and the columns. And then the exterior of the walls would be some sort of brick or other non-combustible material. And the performance of these buildings has been demonstrated throughout history. The performance of them is good. And we have a saying that says, if it's not broke, don't fix it. So with type 4 heavy timber buildings, the provisions were not changed in the 2021 IBC, but they are what influenced the creation of the mass timber building types, which we'll outline, which are type 4A, B, and C. So first, today I'll talk a little bit about the Tallwood Building Ad Hoc Committee and their work and some of the consensus process that they undertook. And then I'll close it out with the new construction types and what they look like in the building code. So as I mentioned, this committee on tallwood buildings, this ad hoc committee, was established by the International Code Council in December of 2015. And their goals were to explore the science of tallwood buildings, to investigate if they were feasible, and if they were feasible, to take action on developing code changes for tallwood buildings. And this was a very robust committee. It was a consensus committee with a balance of stakeholders. And when we say consensus, we mean that everybody on the committee had to agree to any changes before they would be implemented. And this was a group that was made up of experts from across the country, both geographically and from various building construction material industries and areas of expertise. So we had experts in the building code, we had experts in the fire code, we had architects and structural engineers, fire protection fire protection engineers and other fire protection experts, and other construction related professionals whose input was monumental in getting this effort across the finish line. There were several work groups that were created as part of this committee, and primarily today we're going to talk about the work group, or the work done by the fire work group. The fire work group created fire test scenarios to study and to validate these tallwood building change proposals. And the largest test that was done by the fire work group was a full-size 2-story condo or apartment style structure. The interior dimensions of the apartment area are about 30 feet by 30 feet, which is about 9 meters by 9 meters. And the structure also had a corridor and a stair. When deciding how much stuff, for lack of a better word, was going to be inside of these apartments, a research study that was done in North America by an organization called UL, we determined a modern furnishings fuel load was an appropriate one. And we used a fuel load that was approximately the 85th percentile of a residential fuel load, which is called a Group R fuel load in the building code. So this is what the building looked like before we started setting it on fire. The purpose of these tests, again, was to perform tests of a realistic fire scenario applicable to tallwood construction, and they wanted to evaluate 2 main things: occupant egress and firefighter tenability for suppression efforts. And this means we wanted people that were in the building to be able to safely get out, and we wanted firefighters to be able to safely get in to fight the fire. This test was done at a U.S. government facility. The Bureau of Alcohol, Tobacco, and Firearms are the ones that own the facility. And it was also supervised by U.S. Forest Products Laboratory staff. That's a division of the United States Department of Agriculture. There were also several other individuals who were present for these series of tests. I was actually able to witness the first one, but they were done on separate days. So different folks witnessed different ones. Here's the picture of a CLT panel being lowered into place on the test structure before, as it was under construction. This particular panel that we see attached to the crane is about 40 feet long, and that's in the neighborhood of 11 or 12 meters, a little less than 3 meters wide, and about 200 millimeters thick. And it weighs about 6,000 pounds. And that's, I don't know how much that is in kilograms, I'm sorry. But it was very heavy. So CLT, cross-laminated timber, can be used in either a horizontal application like we see here, where it's the floor ceiling assembly that's being lowered into place, but we also see it applied in vertical applications like walls. And this structure, we also have present other mass timber elements, including glue-laminated timber beams and columns. So this test actually tested not just cross-laminated timber, but other mass timber elements. So you can see on the right side of the screen an illustration of the floor plan of one of these apartments in this two-story. The first and the second floor had the exact same layout. So we had a test plan that included a total of 5 tests. And the first 3 were the unlikely scenario in which an automatic sprinkler system that is present would fail to activate, and then there would not be any response by the fire service. Test 4 was a little bit more realistic. This is where we would have a normal sprinkler activation, and this test only lasted about 6 minutes. And test 5 was a situation where the assumption was the automatic sprinklers failed to activate, but are later manually charged by the fire service. The other important thing for all of these tests was that each type of proposed building, or each group of proposed building type, it's kind of a weird way to say this, was represented in the fire test scenarios. So it wound up with 3 new proposed building types that wound up in the code, and each of them was represented in at least one of these 5 tests. So the first test is the baseline test. This is akin to a type 4A structure where all of the mass timber surfaces are protected with 2 layers of 5/8" thick type X gypsum wallboard. And what type X gypsum wallboard is a cementitious board that is applied over the mass timber, and it's considered non-combustible. And this also establishes a baseline for a structure where no mass timber is exposed and will not be contributing to any sort of fuel load. Tests 2 and 3 both had a little bit of the CLT exposed in the living room and the bedroom areas. Test 2 had some of the ceiling area exposed, and test 3 had 2 of the walls exposed. And we can see in these first 3 tests, they were pretty long in duration, between 3 and 4 hours. So these tests were allowed to run until the fire ran out of contents or fuel to burn and went into what's known as the decay phase, where it's no longer gaining any energy and is starting to extinguish itself. The last 2 tests represented a type 4C structure, and that's where all of the mass timber surfaces are fully exposed. And in test 4, as I mentioned, the sprinklers activated normally. And in test 5, the sprinklers had a 23-minute delayed activation. And we'll talk about why we picked that number, that 23 minutes, in a little bit. Looking at the structure again, here's a rendering, 3D rendering of the wood elements present in this structure. So as I mentioned, it's a 2-story structure with 1 apartment per level. And each apartment is roughly 30 feet by 30 feet, or again, 9 meters by 9 meters. The height of the ceiling is 9 feet, which is just shy of about 3 meters. And we used what's called a 5-ply CLT. That means there's 5 layers of Douglas fir larch lumber in that cross-laminated timber panel. Each ply, or each lamination, is 1.375 inches thick, and that is around 35 millimeters. The whole thickness of the panel is 6.875 inches, or around 175 millimeters. The layers, the laminations are connected with a polyurethane adhesive between them. And as I mentioned, again, there's a corridor around each apartment and a stairwell in the back. Looking in when it's a little bit more of a finished type structure, to give you an idea of the layout of it. And when I start talking about, the kitchen side versus the bedroom side, in between the 2 sides, we have 2 main areas. We've got a kitchen and living room. And if we're looking at this top illustration here, it's the area that is the leftmost room, and the bedroom and bathroom area would be this rightmost room. And since most fires are found to start in the kitchen, when we look at the fire tests, we will see the point of ignition does occur in the kitchen. Each of these 2 rooms is roughly 15 feet by 30 feet, so about 4.5 meters by 9 meters. Between the compartment, or the apartment, and the hallway, the corridor, we have a 20-minute rated door. And then between the corridor and the stairwell, we have a 90-minute rated door. And the partition between the kitchen and living area and the bedroom and bath area, which is shown here, is made of a 1/2-inch unrated gypsum wallboard. And that's different than the type X gypsum that we've used in other places. As I mentioned, the fuel load was selected based on a residential survey that was done by UL, and it's 570 megajoules per square meter was the number, which was about a 23 megawatt fire. And going in for a typical tour of what it looks like after it's constructed, but pre-testing, we see that a good portion of the fuel load was achieved through a combination of typical residential furnishings. We have combustible floor coverings, we have combustible cabinetry, and other contents that can combust. But even with all of the furnishings and the contents, we still found that it was necessary to add additional load to achieve that 570 megajoules per square meter. So we see in certain instances the addition of wood cribbing on top of the desk here. You can see quite a bit of it. Next to the bed in the center bottom illustration, you'll see some additional fuel around that. So that's why you see those pieces of wood present to obtain the necessary fuel load. And then this shows the top floor apartment that we tested that had some of the ceiling exposed. Also of note, we have a soffit, which is common in kitchen construction, where the ceiling is dropped slightly to accommodate for utilities or other things. In mass timber structures, we cannot have mass timber exposed in concealed spaces. So that's why we do see these steel studs present in this top left photograph here. Additionally, each unit did have plumbing, mechanical, and electrical penetrations, but the utilities themselves were not actually connected. But the penetrations were protected as required by the current code to make sure that those requirements were effective when used with mass timber structures. So as I mentioned, test one, the first test we did was our baseline test where none of the mass timber was visible. It was all protected with 2 layers of this 5/8 inch thick type X gypsum wallboard. And this is an illustration of the test beforehand, and I have some pictures. So as I mentioned, the ignition occurred in the kitchen area, which would be as you're looking at the structure, the room on the left of the apartment. In the top center picture, we see a phenomenon known as flashover occurring in the living room and kitchen area. Flashover is something that occurs when the air in a compartment reaches around 500 degrees C. That air is superheated such that everything that is in contact with that air catches fire or ignites. So the compartment flashes over, and we found in this test, the first flashover occurred around 12.5 minutes after ignition. Around 17 minutes after ignition, we saw flashover occur in the bedroom area on the right side as you look at the structure. And then the bottom center and the bottom right photos show the condition of the living room and the kitchen following the test. So we've gone through our decay phase where the fire was allowed to burn without intervention. It consumed all the fuel in the compartment. And then we found that the combustible contents, once they were burned through, there was no additional fuel. The mass timber elements did not become involved or contribute to this fire in any way. And I do have a video of this test. Let me go ahead and drag this over, and we are going to keep it muted because the sound isn't so important. And if you are interested, the link that we'll show on the slide has a link to our YouTube channel where we have videos of all 5 of these tests. But in my opinion, this one's probably the best one. It was the kind of most intense heat that was measured from all of them. They were all pretty close, but this one also was the first. So we thought we knew what to expect, and the results were in line with what we had modeled, but we also had that element of we weren't 100% sure. So we see that we're approaching flashover in the living room compartment. As the flames propagate across the ceiling, the air becomes superheated, and then the contents will ignite. And then as we then approach the second compartment, then starts to contribute, become part of the fire load. We see on the thermal image in the left side of the screen, we can see the ceiling heating up as we approach flashover in the second compartment in the bedroom. And there we go. There's our second flashover. Again, that happened about 17 minutes after ignition. So the rest of the test was less interesting from this point out. We just kind of had to sit and wait for it to finish. So we've got this time lapsed here. We do have some videos showing the performance of the fire-rated door, which was a 20-minute rated door, and it failed just about 28 minutes. So in line with the performance that we would want. And then as the intensity of the fire starts to die down a little bit, some of our cameras were able to come back online. And there we see the test terminated at 3 hours. All right. Let me get that out of the way. All right, awesome. So test number 2, this was a similar test in that we had some of the CLT covered with that type X gypsum, but we had 30% of the ceiling area in the living room and bedroom areas exposed. We had live load applied on the top of the structure using water barrels, which was in line with the residential design load that was used in the structure. And this again was in line with the type 4B construction, where some CLT is allowed to be exposed, but the remainder must be protected. And again, we have some photos of that test. Ignition again in the kitchen, both compartments flashed over, almost exactly the same amount of time after ignition. The living room kitchen area was again 12.5 minutes, and the bedroom was at 17 minutes, so almost to the second. We see the decay phase here in the bottom left, and then the bottom center and bottom right illustrations show the CLT panels that were exposed during the test. When we see the type X gypsum wallboard removed after the fire test, we're able to inspect the condition of the protected CLT as well as the protected glulam column and beam after the test. The portion of the ceiling that was exposed is shown. It's a little bit chopped off in this photo, but it's just above the gentleman standing on the ladder there with the white hard hat. Again, the areas protected with the gypsum wallboard were largely uncharred, with the exception of a little bit of limited charring just at the corners of the glulam beam that was noted here. But the remainder of the mass timber elements remained largely intact. After the fire, the section of mass timber that was exposed to the fire was removed and replaced for the next test, and sections of that panel were sliced so they could be more closely examined. And here's an obtuse kind of angle, not exactly straight on angle, of the panel that we see after the test. We see a char layer that we call kind of an alligator skin pattern, because it does look a little bit like an alligator hide, is clearly visible, and the protection of the inner layers by that insulating char is noticeable as well. Looking at another cross section, once the char is knocked off, we can see more clearly how much of the material did remain intact after the test. In this particular illustration, we see a portion of the CLT is not damaged on the right edge of the photo, and that portion was protected by the gypsum wallboard. The portion that was unprotected is more towards the center and the left, and we do see we have lost approximately 1 full lamination, or about 1¼ inches, which 30 millimeters or so but the remaining 4 laminations are relatively intact. Fire test number 3 was where we had 2 opposing CLT walls exposed, one in the bedroom and one in the living room. So they're on the extreme opposite sides of the apartment space. And you can see this layout showing which of the exposed walls, or which of the walls were exposed. The center partition, which does separate these 2 rooms, and it has in each of these tests I mentioned, has an unrated gypsum wallboard covering of it. It does not need to be fire resistance rated because the glulam beams and columns are actually carrying the load. So the wall itself is non-load bearing. Test 3, again, done on the top story of the structure. We had flashover occur in both compartments around the same time as the first 2 tests, and the fire was allowed to progress without intervention all the way through the decay phase and through burnout. Test number 4 was the first test we did where all of the mass timber surfaces were fully exposed in the bedroom and the living room. So we can see the ceiling, the walls were not protected with that gypsum wallboard that we had used previously. In this case, the sprinklers activated normally, and that was around 2.5 minutes after ignition. And within 6 minutes, the fire had been effectively extinguished. You can see the extent of the fire damage in this photo here in the bottom center. It was confined almost exclusively to the kitchen cabinet where it was started. There was some smoke present in the other rooms, but there was not any sort of heat damage. Test 5 is again another test where all of the mass timber surfaces are fully exposed in the bedroom and the living room areas. There was a delay in the activation for the sprinklers, which was 20 minutes after the activation from the previous test. So the previous test, the sprinklers activated around 2.5 minutes after ignition. We added 20 minutes to that time, and we got roughly 23 minutes. So that's how we picked the activation time for the sprinklers. And this is again representing if the sprinkler system did not automatically activate, but was subsequently charged by the fire service, the firefighting crew, upon their arrival at the scene. So there was flashover reached in the kitchen compartment during this test, and the bedroom area was close to reaching flashover, but it did not reach flashover before the sprinklers were activated. Within 7 minutes of the activation of the sprinklers, the fire went from the fully developed stage to being effectively suppressed, which is what we see in the bottom picture here on the right. And so here's a brief event log summary for all 5 of the tests. We see that the flashover conditions in the living room and the bedroom were all fairly consistent, roughly 12 to 13 minutes after ignition for the living room and 17 minutes in the bedroom. And this is despite the presence of different amounts of exposed mass timber. The time that it took for the flames to breach the 20-minute rated door into the hallway was higher for tests 1 and test 2. Test 3, we noticed that there was a door frame installation error. So the premature failure of the door in test 3 compared to tests 1 and 2 was attributed to that error. Prior to the test, I mentioned we did some modeling, and it's always nice when your computer model agrees with the real data that you see in real life. These particular models were conducted by some fire professionals at the Research Institutes of Sweden. That's an organization also known as RISE. This particular graph is from test number 2, where we had 30% of the CLT ceiling exposed. The solid black line represents the predicted heat release that the model showed, and the blue line shows the measured heat release during the test. So the behavior of the test was consistent, fairly consistent with the predicted behavior. Additionally, modeling was conducted to predict the ceiling gas temperature. And this again is data that's based on the test number 2 model. And we saw that the predicted behavior and the actual behavior were very accurate. So again, each new construction type that I've talked about has been tested in at least one of these 5 ATF tests. This fire test plan was developed by the Tallwood Fire Work Group. However, there was another work group that had some additional input into this test. This was the structural work group. And these the structural work group had some generic connection designs that they wanted tested in this fire testing as well. So there were also structural connections being evaluated in this test. And I mentioned we tested both mass timber, cross-laminated timber panels, and other mass timber elements, including glue laminated timber beams and columns. If you want a full report of all of those tests, we have a very robust document that was published by the United States Department of Agriculture, and a link to that is available on our website, awc.org/tallmasstimber. And again, videos of all of the fire tests are also available on that website. So after all of that testing, all of the data was collected, other code changes were reviewed. There were 14 total code change proposals under what's known as a Group A code change. Hundreds of code sections were reviewed, and eventually the committee decided on the 3 new types of construction that I've alluded to, type A, B, and C. These construction types differ primarily in their height and the allowable area. So there are limits for these buildings in the code that are listed in both feet. Sorry, we're not on the metric system. And then we also have the height limited to number of stories as well. There are also limits on the area, the footprint of the building in the International Building Code. And there were multiple new requirements for safety during construction for these buildings as well. 2 of the important definitions that came out from this committee are the definitions for mass timber, which we can see here, structural elements that consist primarily of solid, built-up, panelized or engineered wood products that meet minimum cross-section dimensions. And those minimum cross-section dimensions are important because they are based on the historical Type 4 heavy timber minimum cross-section dimensions. So we didn't really reinvent the wheel here. The other important definition. There were many new definitions added. I'm just focusing on these two today. Is non-combustible protection for mass timber. And in short, for what we will be using in these types of buildings, that's primarily going to be that 5/8 inch thick type X gypsum wallboard that we used extensively in the tests. And that's a product that's used very commonly in the US. It's not a specialty product by any means. Okay, so we went through the work the committee did and all of their consensus work, and what is the actual end result? What were the fruits of their labor? There were 3 new construction types. So I mentioned these already: type 4A, type 4B, and type 4C. We had a construction type in the building code before that was the heavy timber provisions, and that used to simply be known as type 4. That was renamed again, type 4 heavy timber. Nothing else was changed about it. It was working great, and we didn't want to mess with it. There were some references in the code where they've referenced heavy timber as opposed to mass timber. So those references were cleaned up and clarified where necessary. But we've got these 3 new construction types, and we have 1 primary difference between the 3 types, and that is related to how much of the mass timber wall and floor area is allowed to be exposed and how much has to be protected with non-combustible elements. Type 4A has to have all of the mass timber protected with non-combustible elements. Type 4B, we have limited elements of mass timber that are permitted to be exposed and not protected with the non-combustible protection. But there's limits on how close they can be and how big the areas can be. Type 4C allows for all of our mass timber surfaces to be exposed. So our floors, our walls, our ceilings, they're all permitted to be exposed. There are some requirements where you do have to have protection, non-combustible protection in type 4 buildings. That includes things like shafts, elevator or stair shafts, concealed spaces, and then on the outside of any exterior wall. For all of these buildings, you'll have to have non-combustible protection. For type 4A, it's required that at least 2/3 of the fire resistance rating for the building elements be from a non-combustible protection. And again, these are our taller buildings, so we're not going to be allowed to have any exposed mass timber. Type 4B limits how much the mass timber can be exposed and how close they can be. And again, 4C has very few requirements on non-combustible protection with certain features. If you look at IBC table 601, this tells you the required fire resistance rating in hours of specific building elements, and it gives it for all of the different building types that are included in the code. Type 1 buildings are the tallest buildings that are allowed in the IBC. And we'll note that for type 4A structures, we have the exact same fire resistance rating requirements for type 4A as we have for type 1 buildings. So we see the primary structural frame needs to have 3 hours of fire resistance. The bearing walls, both interior and exterior, 3 hours. Type 4B and C have the same fire resistance rating requirements as type 1B. So primary frame needs to have 2 hours of fire resistance rating. Your bearing walls are also 2 hours, and your roof would be 1 hour. So when we look at, what does a type 4A building look like? We don't see any mass timber. We have non-combustible protection on the interior and the exterior, and all of the floors must have a minimum of 1 inch of non-combustible material above the mass timber. This is typically achieved with a lightweight concrete topping, also known as gypcrete. And this is good not just for the non-combustible protection that it provides, but it also helps with sound transmission. So if you're on a lightweight floor, it can transfer certain types of sound more readily. So this helps dampen some of that sound. The maximum height that these type 4A buildings would be allowed to be is 270 feet, which is about 82 meters. The number of stories would depend on the type of building or the occupancy class. So for certain occupancies, the restriction is 9 stories, but for other occupancies, you are allowed to go up to 18 stories. Sprinklers are required in these buildings. And as I mentioned, the fire resistance from non-combustible protection is required to be 2/3 of the fire rating. So it's going to be 120 minutes for your primary frame. Type 4B is where we start seeing more mass timber. Visually seeing it, we're still using the same amount in certain spots, but we can look at it now. The maximum height of these buildings is about 55 meters or 180 feet, and the number of stories would range. The maximum number of stories would range between 6 and 12 stories. Again, these structures have to have sprinklers as well. A primary difference between type 4B and type 4A also is the material that the stair and elevator shafts are permitted to be made out of. So if we go back to type 4A, the stair tower is required to be non-combustible. So oftentimes you'll see it constructed from concrete or masonry. For type 4B, you are allowed to have protected mass timber as your stair tower. There is, as I mentioned, language that limits how close the unprotected mass timber elements can be. They need to be at least 15 feet apart, or about 5 meters apart from each other, from exposed portions of other walls or other portions of the ceilings that are exposed. And the intention of this is to reduce the amount of potential heat flux that one exposed area might receive from another in the event of a fire. And then type 4C, this is where we can visually see the most mass timber. All interior mass timber can be exposed. There is certain areas that do have non-combustible protection requirements. So the exterior, the outside of exterior walls is required to have 40 minutes of protection. And while there aren't any requirements for the floor toppings in type 4C buildings like we saw in type 4A and B structures, the floors do have to meet the provisions of IBC section 804. And that's a general requirement that applies to floors of other construction types as well. If we do have mass timber in concealed spaces, it needs to be protected, and you can't have any combustibles inside of those. And shafts, stair shafts or elevator shafts would need to be protected on the inside and the room side with a 40-minute non-combustible protection as well. These buildings would be allowed to be up to 85 feet in height, and that's about 26 meters. The number of stories would range, the maximum number of stories would range from 4 to 9. And again, you can have all of your mass timber fully exposed. These are still required to have sprinklers in them. And there's no specific requirements on floor toppings, but stair towers do need to have the mass timber protected. And if we want to compare all of our type 4 wood and mass timber construction in one slide, this is that slide. So if you take a look at type 4 heavy timber, that's our historic allowable structure, the heavy timber structure, and we saw a maximum building height for many, many years for these structures of 85 feet. Comparing that with a type 4C building, you see the same height restriction of 85 feet or roughly 26 meters. The only difference would be in the allowable number of stories. So the building heights are the same, you can just have more floors in a type 4C building. Type 4B, up to 180 feet or 55-ish meters. And type 4A, around 270 feet or 82 meters. And that is all I have in terms of prepared remarks. I'd be happy to take any questions you might have. And if anyone thinks of a question after we're done speaking today, our email address is here on the screen. We would be delighted to hear from any of you.